We're going to do empirical formulas, which are formulas which show the smallest whole number ratio of our our elements. Now they belong to a group of formulas, so many different molecules may have the same empirical formula. To find the empirical formula here, all you need to do is divide by the least common multiple. So we're going to divide them all by 6. Did I say that right? Least common multiple? Yeah, or the greatest multiple. Because if you divide them by 2, you won't get the empirical formula. That's the empirical formula of glucose right there. So what if I had C12, H24, and then O12? Well, they have the same empirical formula. Okay, you get the idea. So now empirical formulas have a purpose because they help us discover the identity of problems of compounds. But I will get to that when we get to it later. For now, let's just see where we can go. So if we're given a percent right here, a hydrocarbon contains 85.7% by mass of carbon. We want to deduce the empirical formula. So since it says hydrocarbon, that means it has 2 elements in it, hydrogen and carbon, right? A hydrocarbon. If it said a carbohydrate or something else, then it might have an oxygen, but it's only carbon and hydrogen. So we know that we're going to assume that there's a 100-gram sample. So it makes our calculations easier. That means that there's 85.7 grams of carbon, right? So if we assume a 100-gram sample and 85.7 grams is carbon, we can find the mass of the hydrogen, 14.3 grams. Once we know that, we now need to find the number of moles of each of these. Okay, we need to convert these to moles. So 85.7 grams of carbon, grams to moles of carbon. So we're just going to use easy numbers for our molar masses. 85, that's going to be 7.14. And we'll do the same thing for hydrogen. Hydrogen's easy because we're dividing by 1. Molar mass of hydrogen is 1. Okay, let's just make it easy. So you may choose to write that step or not. Okay, so we've got these numbers. These are the moles. Now these are the actual ratios of carbon to hydrogen. Can you see a ratio yet? Probably so. But here's an easy way to see that ratio in an easy way. You just divide them by the smallest number. So 7.14, 7.14. Because not always is it easy to see the ratio. So that is obviously 1. And this is not exactly 2, but close to it. So we'll just round it to. Okay? That is our ratio of carbon to hydrogen. There's 1 carbon for every 2 hydrogens. So that means that our empirical formula is CH2. It's that simple. They do get a little more complex. Let's do this one. We're talking about pure nickel. Was discovered in 1751. It was named for the German word Kupfernickel, meaning devil's copper. A compound of nickel was analyzed and shown to have the following composition by mass. You get your compositions here. We want to deduce the empirical formula by the same thing. We're going to assume a 100-gram sample. This adds up to 100 grams, so these are the only compounds we have. So we'll take our nickel, 37.9 grams, and we'll divide it by its molar mass to find the moles. And then we'll take this is nickel, sorry. This is sulfur, and this one is going to be oxygen. We'll take sulfur, and we'll divide it by its molar mass, 32 grams of sulfur. I should label that. And 1 mole, also label that. And then we have oxygen. It was 41.4 grams of oxygen to moles. Essentially, we're working backwards from what we did last time, but we're throwing some wrenches in the sink. So what we're doing is then this will come out to 0.655, 0.645, and then 2.59. Can you see a ratio? See, sometimes it's not as easy. So all you do is divide by the lowest number, 0.645, that's obviously 1. 0.645, you don't need a calculator. You can tell that that's probably pretty close to 1, right? Sorry, that's a little messy. And divide by 0.645. And we will find that that one is actually pretty close to 4. So we'll round that all. So we'll have 1 nickel, 1 sulfur, 4 oxygens. That's an empirical formula. Let's do one last example with example 6. Add a 2.765 gram sample of lead oxide. Now lead is funny because it's a transition metal, and so it can have different oxidation states. Oxygen is always -2, but this one can be +4 or +2. So it could be PbO or it could be PbO2. So how do we say that? We'll just say subscript of x and y. X and y. X may equal y. We'll see. It was heated in a stream of hydrogen gas and completely converted to elemental lead with a mass of 2.401 grams. What is the empirical formula of the oxide? Well, you may be tempted to write an equation out, right, showing the hydrogen gas, but that's not going to tell you much. What will tell you something is that this sample weighs 2.765 grams, and that 2.405 this many is actual lead. So this is the lead. This is the lead oxide. So the oxygen must weigh 0.364 grams of oxygen. That's the law of conservation of mass at work. So when we take our lead, we will take 2.401 grams, and we'll divide by the molar mass, 207 grams to mole, and we'll get 0.0116. And then for oxygen, you will get 0.364 divided by the Here we go. You don't have to be all that precise, but be kind of close, because when you divide these, you want to get them somewhat close. Maybe 3 sig figs is fine. All right. And so we divide by the lowest common multiple, and this one's obviously 1, and this one is close to 2. So our empirical formula was PbO2. Similar to what we expected either PbO or PbO2. All right, that's going to be it for empirical formulas.